This is Stephen Stanley, Robert Fuller, and Stephen Miller coming at you with temperature control for a constant output Fischer-Tropsch synthesis reactor. We wanted to start by thanking all of our viewers for watching this, and we also wanted to say that we're very excited to present this to you. Because of our experience with Fischer-Tropsch catalysis, we're currently taking kinetics and catalysis from Dr. Hecker, an expert in the field, and so we're excited to show you this.
So a significant problem with Fischer-Tropsch or gas-to-liquid processes is that the catalyst deactivates over time, making constant production difficult. We wanted to achieve this with having a control variable of production, and the easiest and cheapest way to do this is by varying temperature. It's an exothermic reaction. You can get it as hot or as cool as you want. We had a manipulated variable as temperature, and we did this by modeling the activity over time with the temperature varying throughout.
Now Stephen Stanley is going to take us away.
All right, so this is the model that we used to calculate the rate of our reaction. We got this data from Dr. Hecker's lab, or these rate constants that have temperature dependence as well as pressure dependence. And we also got deactivation rate from Dr. Hecker's lab that says how quickly the catalyst deactivates over time. Now this term is going to be over hour or month time scale, hours to weeks to months. And so it's really difficult to model this in just short-term timescales, and so we needed to go to Simulink to do this over long periods of time. And we also, in our reaction, had a selectivity expression that tells us how much of the reaction goes towards methane production and how much goes towards other higher hydrocarbon productions. And so what we did was we modeled our packed bed reactor as 25 CSTRs in series, and this is a good approximation for low conversions per CSTR. Where your inlet concentrations are practically equal to your outlet concentrations, so you can approximate the reaction conditions as your inlet concentrations.
As well, there's a little bit of dynamics that go into when you change the temperature and when the reactor reaches steady state. From also experience in Dr. Hecker's lab, we used a transfer function with a time constant of 1 hour to approximate the transfer function of temperature changes, as well as a 5-hour time constant for approximating the reactor dynamics.
So here's a look at what our Simulink model looked like. We have our first reactor here that takes the input pressures and temperature and reacts it and gives out the unreacted reactants as well as the product. And this also feeds into an activity function that calculates the change in activity over time, and it integrates this and gives it back to this reactor. And as you can see, all of this gets passed down the line to the next reactors here. Up here we have the remnants of our step tests. The output port isn't connected because we now have our PID connected, which is working pretty well.
This graph represents how activity in our simulator changes over time, and we used a 3,000 hour time scale for this simulation. The activity at the beginning of the reactor is modeled by this yellow line, and at the end of the reactor it's modeled by this blue line. Since we are using a packed bed reactor, the activity changes with length in the reactor, so we can see the lines in between the blue and the yellow are all varying activities within the reactor. Next, we performed a doublet test by changing temperature, which is represented by this blue line, and we received data from this doublet test, which is in green. We then tried to fit a FOPDT model to it, which is in red. As we can see, these do not match up perfectly. This is because activity varies non-linearly with temperature and time. However, when we minimized error, we were able to obtain a gain, a time constant, and a dead time that we're able to apply to ITAE parameters.
So we initially used the ITAE set point tracking tuning parameters that gave us a P and I as shown. It had a good rise time, but the settling time and overshoot was a bit high. That's shown by this blue line here with the respective green temperature curve. And we wanted to reduce the overshoot because this is an exothermic reaction. You don't want any runaway reactions happening. So we reduced the regressiveness of the controller with the P and I values as shown, and that reduced our settling time, increased our rise time a bit, but significantly reduced our overshoot. That's shown by this orange curve here for our production, and then the red curve here for our temperature.
In conclusion, we successfully implemented a PI controller to maintain constant production by varying temperature over large timescales. Thank you very much for watching our presentation.